This is Unit 1, Section 1.6, and this is kind of wrapping it up using tests wisely. And so what we're going to start looking at to wrap up Unit 1 is inference. So once we've done a survey, once we've done an observational study or an experiment, what do we do with the results and how does it apply to a larger population? So the design of these is really what's going to be able to tell us how we can apply it to a larger group. One thing that we're going to touch on is also the ethics in data and cause and effect. So things that we can say, but we can't necessarily, do because of morals and ethics involved in experimental design. After this, we're going to review, getting us ready for our first unit test. All right, so one of the things that we're going to be discussing today is inference, and that's conclusions about the larger population and or the cause and effect that go beyond the actual data, which can be safely made with two different things. We need to make sure that bias has been eliminated by random assignment and that the differences are too large to be explained by chance alone. So meaning this isn't just something that happens occasionally. This would be something that is so large that it's a significant difference. And statistically significant means that it didn't happen by chance alone. It happened because of the treatments that were in there. So what this means is if we do our experiment and we've made sure that we have no bias because we have random assignment of our treatments, we've addressed the placebo and the placebo effect, we have kept it single blind, maybe double blind if we're able to, and if we needed to block, we blocked. If we needed a match pair design, we did a match pair design to improve our completely randomized design if we needed to. The difference is if we see differences here that they can't be just happen by chance in our groupings, we can say that we have cause and effect, that our treatments cause the effect of our response variable. And that's the overall goal of experimentation, is that we have this hypothesis in mind of what we're trying to see. However, just because we made the hypothesis doesn't mean that the data is necessarily going to report it. In the next coming units, we'll also talk about how we can kind of manipulate the data to kind of look at how we want to present it as well, and how we can paint a picture that might be different than what the data actually says. So again, ethics a little bit today too. So here's a chart that explains kind of how do we apply inference? How can I go beyond just the data that I've collected? And so when we look at our groupings here, we can have, were our individuals randomly selected? And so this is what we really want to do when we're doing surveys. Okay, on the second one, were the individuals randomly assigned to the groups? So typically we randomly select our individuals for surveys, but then we can't infer further than the group that we actually picked from. So this wouldn't be an experiment if it was just yes here. So if we have yes, we did randomly select our individuals, then yes, we can make inferences about a larger population. Okay, if we also randomly assign them to groups, then yes, we can make inference about cause and effect. Okay, because both of these are yes, we can go further than just the data that we collected from. So if I sampled randomly from SMS population and I assigned my sample to those groups, I could make these two conclusions. Okay, I can always make inference about the population if my individuals were randomly selected. However, in this case, if I do not randomly assign to groups, if I've let them pick that, or if it was an observational study, I cannot make cause and effect. Okay, so this would only be an experiment here. And since I didn't randomly assign treatments, I can't make cause and effect inference. And then if we continue, we would have this one being now no. We did not randomly select, but we did randomly assign. This would be most experiments where we have volunteers not randomly selected from the population. So we can't go bigger than the population that we've chosen from. The inference, though, we can start to establish cause and effect if we've randomly assigned and have results that are statistically significant. And then in this case, this would be a no and a no. So sometimes this might be an observational study where I observe conveniently the students that I have in my class, but I also haven't assigned them random groups. I'm just observing things. So I couldn't say what happens in my fourth block necessarily applies to every AP Stats class I had because I haven't randomly selected them. And then cause and effect, I couldn't say, oh, well, just because they had their phone out, now their homework scores are bad. I couldn't say that was absolutely the cause because I did not randomly assign people to do or not do their homework. So an example here, it says we have, let me move that down just a little bit. Vitamin C and canker sores. A dentist wants to know if a daily dose of 500 milligrams of vitamin C will result in fewer canker sores in the mouth. She designs 4 different studies. Explain what inferences are safe to make in each design. So her first design says survey all her patients with appointments in the next 2 weeks on 1, if they take at least 500 milligrams of vitamin C each day, and 2, if they often have canker sores. Divide the patients into 2 groups based off their yes/no responses to that first question. So in this case, was it randomly selected? No. She just let people come to her. Those next 2 weeks, anybody with patients. Did she randomly assign the medicine? No. So we can't make any inference here. Not about her population as not large, and we also can't make cause and effect that maybe the vitamin C causes fewer canker sores. We can't make that inference. And the second design, it says all her patients with appointments in the next 2 weeks are randomly assigned to either take 1 500 milligram of vitamin C each day, or 2 take no vitamin C for 3 months. Random selection, still no, because she's still taking those appointments with the next 2 weeks. And then random assignment, yes. So she has randomly assigned that. So we can say it's now cause and effect if the results are significant, but not to the population. So it won't apply to everyone. This would only apply to those people, saying there was a cause and effect relationship for those patients that she had in the previous 2, or in the next 2 weeks, I guess. The design 3, survey randomly selected dental patients from town on 1, if they take at least 500 milligrams of vitamin C each day, and 2, if they often have canker sores. Divide these patients into 2 groups based off their yes or no responses to that first question. They are randomly selecting, but they are not randomly assigning. So we can infer about the population, but we can't say what caused it. So we might be able to say, hey, there's a correlation between taking vitamin C and having fewer canker sores, and we can apply that larger than our group that we started with, but we can't say that the vitamin C caused the fewer canker sores. So no cause and effect. And on the last design, it says randomly selected dental patients from town are randomly assigned to either take the 500 milligrams of vitamin C or take no vitamin C for 3 months. This is random selection and random assignment. So we can say this does have cause and effect if the results are significant, and we can say about the population. So we could say if the results are statistically significant, we can say the vitamin D caused the fewer effect, which would be our canker sores, and we can say not only does it apply to our group of randomly selected dental patients, but this should apply to everyone in the population. And so this would be, if possible, the best way that we could do that. And then the last idea here, before we move into ethics, is sampling variability. And this is the idea that when we take a sample, it might not match the population number perfectly. Because we have sampling variability, the sample and the population still might be slightly different. Even if we've done everything we can here, sampling variability is a way that we can say we didn't have bias, we did everything that we could to control. They still might not match exactly. This variability is the idea that different random samples from the same size, from the same population produce different estimates. One way that we can start to reduce the sampling variability so that when I have my first sample and my second sample that's trying to predict what this population measure is, what I want to do then is reduce the sampling variability by increasing our sample size. And so what this does is makes the sample more similar to the population. So the closer I get to the population, the more reliable and consistent my sample will be. This is always a good thing. If you can have more patients, more subjects, more experimental units in your survey, observational study, or experiment, you will always get more reliable and more consistent results if it was replicated. That's going to be a big thing that comes up a lot. How do we reduce that variability? Let's get more involved. Let's get more options and more data points. So an example says, how much do DFL players weigh on average? And a random sample of 50, okay, I knew that was not supposed to be DFL. I was like, what in the world? How much do NFL players weigh on average? In a random sample of 50 NFL players, the average weight is 244.4 pounds. Do you think that 244.4 pounds is the true average weight of all NFL players? And in this case, I would say no. Sampling variability will give a close estimate, but not the exact number. So in the past, I've had students that would answer this and say, no, because people could have lied about it, or they only measured the light people or the heavy people. And that doesn't, they say here, this was a random sample. And while it is possible that it was all the heaviest or all the lightest NFL players, it's not likely in a random sample. So the reason why they aren't exactly the same is just sampling variability, that we don't have access to the entire population, and so this is an approximation. On B, which would be more likely to give an estimate closer to the true average weight of all NFL players, a random sample of 50 players or a random sample of 100 players? We would want to use 100 players. And the reason would be increasing our sample size will decrease the variability. In our sample. Okay, so if we've now decreased the sampling variability, this will give us closer to the true average. So sampling variability is something that we want to consider as we're designing our experiments or surveys or observational studies, that the larger the sample, the better. But we also want to make sure that we're considering that we don't have access to the entire population and that our sample might not match exactly. We want to do everything that we can in our design and our sampling to make sure that we have the large enough sample to estimate well. And then the ethics of data, their basic principles is do no harm. Studies have to be approved by an institutional review board. We must have subjects have to give informed consent, and individual data are kept confidential. So some basic principles, that idea of you can't harm something. And that's why we have lots of organizations that protect animals, that protect wildlife, that protect humans. As far as being part of an experimental study, you have to be very aware of what you're agreeing to when you sign up to be part of an experiment. So look at these 3 scenarios here and decide if you think these studies are ethical or unethical and explain why. And really, there is no correct answer here. Your answers are going to vary based on what you think is ethical or unethical and how it was set up to kind of begin with. The last part here is sometimes an experiment might not be possible because it's impractical or unethical. So if we can't set up an experiment, we can't imply causation. So we've heard this phrase where it says smoking causes lung cancer, but there's never been an experiment done on this. What we could conclude is the association between smoking and lung cancer is strong. The association between smoking and lung cancer is consistent. Okay, we could say larger values of explanatory variable are associated with stronger responses, meaning the more you smoke, the more likely it was that you got lung cancer. But what we can't say is causes, okay? The alleged cause precedes the effect in time. What this kind of implies is we didn't set up an experiment and say, okay, here's my 60 volunteers. Oh, you not a smoker? Too bad. You've been randomly assigned to smoke. And then we have our non-smokers here. Okay, we can't randomly assign that. And because we want to compare these results on lung cancer and see what are the results here, this is not an experiment. We could do observational studies that look into people that smoke and don't smoke and the effects on lung cancer. But because we can't set up an ethical experimental design here, we can't say it causes because we're not randomly assigning the treatments. And that's what it goes back to here. If we cannot randomly assign to the group, we cannot make inference about cause and effect. So even though people use this kind of haphazardly, this word causes, we need to make sure that they're in statistics and in the science world, and we need to make sure that they are using that appropriately. Smoking causes lung cancer. Is it an accepted idea? Yes. But the better way would say there's a strong association. It is consistently shown that there's larger values of the explanatory smoking that are associated with stronger responses of lung cancer. Those are ways that we can still say and relate those 2 ideas, but still not apply causation. So we have to be careful about that. Okay, our practice tonight, make sure that you email me if you have any questions, and have a good one.